Good evening, everyone, or good afternoon, depending on where you're joining us from in the country, or I see a couple people that I believe are from the States as well, so thanks for joining. This week, we're going to be talking about sections 2.4 to 2.5.20 of the body of knowledge, which is about network design, architecture, and telephony concepts. I'm Justin, current second vice president with NENA Ontario, and Deputy Chief with Barrie Fire Emergency Service in Ontario. So thanks for being here tonight. Jamie, can I have you just accept people for the next little bit? That'd be great, thank you. So tonight's presentation, we've broken it down into kind of 4 sections. So section 1 is going to be about the public telephone network and E911. Section 2 will talk about call routing and the underlying technology with that. Section 3 will talk about reliability and redundancy. And then section 4 will be transitioning to IP. About tonight's session, a lot of this is going to be quite complex concepts we're going to be talking about tonight. So I'm hoping I can explain everything in the best way possible. We will be focusing on the content from the body of knowledge, which might not necessarily be exactly how we're doing things in Canada or things you're seeing operationalized here in the country, but definitely important if you want to pass the exam. That's what we're trying to focus on here is the body of knowledge. You'll probably want to do some research after today's session on some of these concepts to really nail them as best as possible. But I'll try and be as basic as possible throughout this presentation, and we do have lots of graphics in this presentation. Stop me at any time for questions, comments, anything anyone might have to add. Please, it's an open forum here. Please feel free to do so. And while most of these concepts we're going to talk about tonight are focusing quite heavily on the E911 environment, there is a little bit on NG911. And for some of the acronyms and terminologies we're going to be talking about, the NENA glossary is also a great tool to reference at times as well. So starting with our introduction to the E911 network architecture, this section is going to give us the baseline for how 911 calls move throughout the telecommunications network. Everything from selective routing to NG911 architecture is built on these older systems. The underlying legacy design, which includes the transportation, the switching, and the LADAs, which we'll talk about. And we can see why call routes the way that they do, and why NG911 needs a bit of a different approach to make this all work. So on this slide, we have the legacy telecom design shapes today's 911 routing based on the public switch telephone network, so the PSTN. Underlying that will help us understand the transportation switching and LADAs, like we said, and the routing involved. As far as transportation, think of transportation like connecting the dots on a puzzle type thing. The job is to move a call from point A to point B in as few steps as possible, reducing the hops and the resources that it takes to get the call from point A to point B. The transport classification describes the path a telecom carrier uses to push the traffic through the network in the most efficient way. A LADA defines the geographical boundaries where a local telecom provider is allowed to provide services for. So any call that stays inside the LADA is considered a local or intra-LADA type call. And once a call crosses a LADA boundary, it's treated as a long distance call and often handled or is handed off to a different carrier at that point. This is the largest defined geographical area within a network. And the next slide will drill down deeper into the geographical area. So if we want to look at Bell, for example, Bell has a very large primary territory. We got TELUS and many other carriers, but calls within their LADA would be an intra-LADA type call. Once we're traversing that, we're going inter-LADA, becomes long distance calls. When a call originates in one LADA and terminates in another, so going from point A to point B, it becomes an inter-LADA call, a long distance call essentially. These are carried by IXCs, which are the interchange carriers, and think of those as the long distance carriers who bridge the gap between the LADAs. So in this graph we're seeing here, we have one LADA up here, let's call that Bell. We got another LADA here, let's call this TELUS. And we have several different inter-exchange carriers that are helping ensure that call gets from point A to point B inter-LATA at this point. A local exchange is the area served by an end office. So this is when we're starting to get to homes and businesses. It defines where the local calling begins and will usually end as well. The local exchange carrier provides the actual dial tone and manages the customer lines within its franchise area. So these would be an inter-office type call. So in this change, we have a local exchange carrier in the Toronto area that's delivering signal directly to a phone set sitting in a house or a business. We have the ICXs, which are then zooming out on the map that help connect the calls from this local exchange to another local exchange, which could be intra-LATA, which is inside a Bell's network, or inter-LATA if we're crossing several networks. So this local exchange, we're now drilling down to very localized, the actual connections getting into a house or a business at this point. Next is the local loop. So the local loop is the wiring that connects the customer's phone or the PBX phone system in a business concept to a central office through a local exchange. The important part here is the demarcation point, which is where the TSP's responsibility ends and the customer's responsibility begins, usually at the building. So in this case, it would be this wire right here is the local loop that is actually connecting the central office of this exchange carrier to the phone at the house or the business, usually a demarcation point on the building, which is where the carrier's wiring will stop. And then within the building becomes our responsibility as consumers. And then switching determines how calls are going to move through the network. So when you place a call, the switch reads the digits you dialed and decides the next place to send the call. This process continues until the call reaches its destination. And what was a manual process at one point when we had switchboard operators that had to connect all the pins and cables together to get a call from point A to point B. This is now a very automated system that happens within end offices and central offices and IXCs, but it reads a digit and it starts to connect all the dots together to ensure that it gets through all the different systems and all the different carriers to get to point B at the end of the day. Next is the different types of switching. So there's several different types of switches that allows that call to get from point A to point B like we saw in the diagram before. So the central office houses equipment and connects the subscribers. So the central office is in all of our communities. The end office is the class 5 switch that provides dial tone and connects customer lines. And then we have the access tandems where it concentrates the traffic and links end offices together. So if we look at this again here, so end office class 5 is the central office that's connecting homes and businesses. And then a tandem office, which is a class 4, connects the central offices together. So here's a tandem office in the middle. We got all these different towns, let's say with a central office. They're all being connected together by the tandem office. And then we have the homes and businesses connected to the central office with the access loops here in the middle. What we then have is the access tandem, which is the traffic aggregator that connects all the carriers together. So starting from the most localized, being our central office, it then goes to an end office, which goes to a tandem office, and then the access tandem, which is connecting our carriers together. Next, we got our facilities that help transport these connections. So facilities refer to physical assets. They could be cables, switches, or buildings. And the transport facilities refer to the actual paths traffic used, like trunks or microwaves. It's important to distinguish these when diagnosing issues or planning upgrades from a network perspective. And so when we're talking about actually using trunks or fiber or copper, these are physical assets, and then we got things like we're talking about microwave that could be for cellular connection or used in other critical systems as well. And then switches use the primary path to route calls. If that primary path is full though, the call is alternatively routed through an access tandem. And this helps ensure calls are completed even during busy periods. So they do have their primary path that they would always like to take, but they can use one of those access tandems that help connect different carriers together as an overflow path if required during busy times and network congestion. And then networks are designed around expected call volumes. So when volumes exceed capacity, blocking can start to happen. Line load control, it can also restrict how many people get dial tone at once to stabilize the network. So when we talk about traffic load and blocking, that's where if you try to make a call, you either don't get a dial tone or you get a busy signal. That's because they've capped that network you're connecting to at maybe the central office or the access tandem to have a certain load capacity to ensure reliability and stability of that network. Then we got the signal path. So signaling varies depending on the type of call that's happening. So again, the intra-LATA calls, which is within one carrier's servicing area, uses one signaling path. Direct inter-LATA, which is our long distance calls, uses another. And then we got international calls that use yet another path. So routing rules determine which signaling system is going to be used. And we've now talked about landline services, and next we're going to talk about VoIP and wireless. So again, we see different signaling type paths described here, but all you really need to know about is it's one type of signaling path for intra-LATA, one for inter-LATA, and then one for international type calls. So moving on from landline type calls to now VoIP type calls, this can be described by these can be provided by third-party dedicated VoIP service providers or also major telecommunication companies like Bell, Rogers, and Telus, who can also provide VoIP services. VoIP is voice over IP protocol, so kind of similar to NG911 concepts, but very different networks. Voice over IP will send voice as digital packets over the IP network, instead of using traditional circuit-based switching like the PSTN public switch telephone network that we previously talked about. So instead of legacy switches, VoIP using call servers to set up, manage, and tear down calls from point A to point B. And VoIP service providers, also known as VSPs, offer these capabilities. A call can stay entirely within a single segregated VoIP environment, end-to-end, or it can leave that VoIP world and also enter the PSTN world through signaling or media gateways, which will connect our legacy, most common type phone systems to this voice over internet protocols. So if a voice is staying within one provider's area, sorry, this is really lagging right now, so I can't see where I'm drawing. It's using the call server to connect the call from point A to point B. So let's say Bell is offering VoIP services, and this caller is calling another phone that is also a Bell call. It'll typically probably stay within this VoIP call server. But if we have someone on a VoIP service that's trying to call someone that's not using VoIP in this instance, and they're on the PSTN, which is our kind of our plain old telephone system type phone line, then there would be this little media gateway in the middle or signaling gateway that would help take the call out of the call server and send it to the PSTN. Next, we got enterprise VoIP or VoIP MLTS. So in organizations, VoIP is usually referred to as VoIP MLTS, which is a multi-line telephone system. Here, the call server sits inside the enterprise network and manages all internal extensions. So think of City of Toronto, for example. They have an internal phone system within the entire City of Toronto Corporation. That can be looked at as an MLTS VoIP-based phone system. And if I'm calling extension 123 from my desk phone, that's probably all residing within our call server in our phone environment. Calls can exit directly over IP out to the internet to make other phone calls or out to the PSTN through a local signaling or media gateway. From a 911 lens, this creates complexities around location, extension dialing, and how calls will reach the public network. So what's important from a 911 perspective is, generally speaking, anyone that has VoIP MLTS type phone systems, they'll probably still have PSTN phone lines connected to that for 911 services, so that it doesn't have to go through a VoIP relay service to get to a 911 PSAP. The PSTN lines can get directly to a PSAP. And then also, there's lots of work happening around this, but if I'm sitting at a desk on the 10th floor of City Hall and my cubicle is right in the middle of the floor, if I'm calling 911 from my desk phone, how is the PSAP getting that location information? Which there's work happening to get to desk level type concepts. It's not quite there today, but it should be at least giving us the building and hopefully floor or unit number within that building. And then we got the commercial mobile radio services, short form CMRS. This refers to wireless carriers whose networks are connected back into the PSTN. So Rogers Wireless, Bell Mobility, all of our cell phones are connected to some sort of commercial mobile radio service network. These wireless networks are made up of multiple cells, each served by a base station. And your phone registers within the network and constantly looks for the strongest signal to connect to. As you move, the network performs what's called a handoff, and it moves your call from one cell site to another without dropping the call. This seamless mobility is critical for wireless 911 calls. Wireless has evolved over time. So historically, wireless networks use different radios and core technologies. CDMA was in some regions, GSM and UMTS in others, and subscribers connects to the towers, which is connected to an access network and a mobile switching center, which helps get the data through that path. Today, these networks are migrating or have migrated to LTE with what's called IMS cores. IP multimedia subsystem cores is what that stands for. LTE, which supports 4G and 5G, dramatically increases data speeds, reduces latency, and supports both voice and rich multimedia. IMS, or the IP multimedia subsystem cores, is the IP architecture behind the scenes supporting VoIP, messaging, video, and other services over IP. And this LTE and IMS environment is the technical foundation under NG911 wireless calls. So a lot of things we are working towards has to rely on 4G and 5G networks for example, RTT 911 to work successfully. That type of technology will not work on CDMA networks or 2G or 3G, which we probably mostly moved off of 2G by this point and have some 3G around, but it is also being phased out to only have 4G and 5G left. To handle growing wireless traffic and coverage gaps, carriers deploy what's called small cells. These are low power radio nodes with short range. A subset of these are called femtocells, which can be installed in homes or small businesses. They connect back to the carrier over broadband, improving indoor coverage and capacity. So major stadiums probably have some femtocells in them. Music festivals might deploy some small cell technology. Where there's high density volume of cell phones and people, there are probably some smaller cells connecting back to the main network. From a 911 perspective, small cells and femtocells complicate location and routing because the user may be far from a traditional macro tower, but still making a wireless 911 call over the same core network. So it's really important when carriers are deploying these networks that there's accurate location data within all of these cells to speak back to the network on where the caller might be calling from. And then we got our transport facilities overview. So similar to wired call transportation, wireless calls also have transportation needs. So transport facilities are, again, the physical media carried from signals between points. They can be carried along analog or digital transmissions, and they underpin everything we've discussed so far. So common examples of wireless transportation would include copper, fiber optic, microwave link, satellites, and coax cables. Each has different characteristics, capacities, distances, cost, and resiliency. But this is all you really need to know at this point. To get into those a little bit more, so the original telephone network was built on copper twisted pair. Pairs are twisted to reduce interference, and large cables can bundle many of these pairs together. With technologies like DSL, copper can carry significant data, but there are limits on distance and noise, which noise could be interference involved with the signal. Coax cable is another medium, so better shielded and capable of higher bandwidths. It's used widely for cable TV and broadband internet, and in some cases is part of the backhaul network for the telecom services. Fiber optics, which are everywhere nowadays. Fiber optics transmit light through thin strands of glass about the size of a human hair. The light switches on and off billions of times per second, representing digital data. So fiber offers huge bandwidth, very low loss over distance, and is immune to electromagnetic interference. Carriers are increasingly deploying self-healing fiber rings. So if one segment is cut, traffic automatically reroutes onto another path, which is critical for 911 resiliency. And then microwave and satellite. So microwave uses high frequency radio links for line of sight transmission. It works over tens of kilometers with repeaters added as needed, but can be affected by weather. Satellite, the microwave with tower in space type technology. Geosynchronous satellites stay over the same point on Earth, enabling fixed dish antennas to send and receive the signals. And these medias can be lifeline for remote 911 connectivity, but they do introduce higher latency, which is the delay in the signal getting from point A to point B, and can at times have weather-related impairments. So these complete the main concepts for the transmission of wireless data. However, the study guide also recommends that you review Newton's Telecom Dictionary, which I will not get into today, but it is recommended you take a look at that at some point. And then about some switching configurations. So switching configurations can vary by geography and demand. In dense areas, multiple switches may be required to handle the full traffic load. Two common models are standalone switches, which is what we're seeing on the left-hand side of that graphic, which serves an area directly. But then there's also a host or remote setup, which is what we're seeing in the graphic on the right-hand side, where a central host controls several smaller remote switches. And these choices affect how 911 calls route and how failures impact service along the way. So a standalone switch will serve several subscribers within its loop distance and holds all of the intelligence locally. So it's like the brains are all there, it's connecting all the people together, it's managing everything within that host. In a host remote design, the host performs most of the call processing, while the remote units are placed closer to the customers or the subscribers. And if the link to the host fails, a remote can enter emergency standalone mode. In that state, it may still complete local calls, and in some designs can continue to place 911 calls over dedicated E911 trunks, but it does get more complicated to ensure the resiliency in this model. So best practice is for PSAPs to pre-plan alternate routing destinations with carriers if possible to support these scenarios. And this is also important messaging that needs to come down from carriers when possibly remote sites are in standalone mode. So a great example I can put into real world terms is an area we dispatch for the PSAP I work at. We dispatch a First Nations reserve, which is on an island, and they follow this format. So they have a remote switch on the island that's connecting back to a host. There was a power failure that caused an issue in that connection from the remote to the host. So people on the island were still able to call each other on the island because they're connected to that remote switch. But they were not able to call 911 in this case because they didn't have dedicated E911 trunks talking back, and they weren't able to connect to the host, which the host would take care of that calling back to 911. So in this case, information from the carriers get passed down that there's a site that's in a standalone mode and they can't complete 911 calling. So then local messaging needs to go out on how to access emergency services at that point. In legacy E911 environments, there are selective routers. This is the brains to the 911 system. So a local central office will send the 911 calls into this switch over concentrated dedicated 911 trunks. The selective router uses routing tables based on numbers or emergency service zones or sometimes other data to send each call to the right PSAP. It also provides features like selective transfers, conferencing, alternate routing paths, and default routing if something was to fail in the network. And then in some edge cases, end offices do extra screening to decide between multiple selective routes. But in that practice, it introduces some risk and in general is discouraged from network design. Telephone network boundaries rarely line up neatly with municipal or county lines. So a town might be served by several different selective routers than what the actual PSAP covers. One option is to build direct trunks from the foreign selective router to the PSAP, but that can be costly and inefficient. And a better option is usually inter-tandem networking or inter-machine trunks, IMTs, that connect multiple selective routers together. This lets 911 calls and transfers to be moved between tandems, kind of removing the physical boundaries from a geographical sense. So in an E911 environment, you might hear a PSAP talk about their 911 trunks. And in my case, when we were on E911, we had 705 trunks and we had 905 trunks based on area codes. So we had multiple different selective routers or tandems that were feeding our PSAP. And if we had to transfer calls between 705, 905, or even 519, IMTs would take care of that connection between the selective routers. Handling features. So the first one would be selective routing. This sends calls to the correct PSAP based on location using the MSEG valid addresses, which is the Master Street Address Guide, the ANI, the automatic number identification, or location objects like Pitaflow in an NG911 concept. And I'm very sorry, but I have 2% battery, so give me 1 second to plug in my computer. Perfect. Now we are back in business. Sorry, so the 911 system does support several key routing and handling features. So selective routing sends calls to the correct PSAP based on location, like I was saying, which could be the MSEG valid address, so the master street address guide, ANI information, your phone number information, or location objects like PIDAFlow in an NG911 environment. The master street address guide is the most common in an E911 environment, used for routing calls, which was originally used for toll-free call routing, but was adapted to meet the needs of 911 at the time. Selective transfers, call conferencing, and one-button transfers let call takers in the PSAP quickly connect to other agencies. This, in layman's terms, is what we refer to it often as your star codes. And then we got alternate routing, which pushes calls to backup location when trunks or PSAPs are unavailable. And then we got default routing, which sends calls to a designated PSAP or third party when location-based routing fails and the network doesn't know where to send this call to. Cool little fact, did you know that Northern 911 is a default operator, and on average they handle more than 30,000 default routed 911 calls for North America. And then in some basic 911 setups, calls route directly from a central office to a PSAP, which is direct trunking, with the PSAP equipment providing conferencing. This is not common in Canada. And then some signaling basics and a term called SS7. So it's a control language on the telecommunication network, which tells switches how to set up, route, supervise, and bill calls accordingly. So in older designs, signaling could be in-band, which means the voice and the signaling share the same path, or out of band, which separates the voice channel from a data channel. And then we got the modern networks, which use common channel signaling, which is the SS7 term. And this is the most dominant protocol used today. A separate signaling network controlling many voice circuits with data at the same time. For 911, signaling carries critical data like ANI information, trunk status, routing details, and location information. Okay, and then we got CAMA, MF, DTMF, and ANI delivery. So CAMA trunks are what essentially collects the ANI information. It was used as a billing mechanism back in the day for toll-free also, but that collects the number information and helps speak to the MSEG database for how to route calls. We got MF signaling, which moves the ANI between switches. And then we got DTMF or MF, which is DTMF is on the user's side that sends tones to the network, or we got MF signaling, which is network to network, which is how different networks communicate together. And then there is enhanced MF, which supports 10-digit ANI data to the PSAP. And then finally, we'll tie all the different transmission types together. So analog is a continuous waveform, the natural form of the human voice. Legacy networks carried analog on the access side, but switching and long haul have often used digital signaling, using TDM to multiplex many calls over one path, so merging bunch of different data and voice calls together over one path. In packet networks like VoIP or NG911, the voice is broken out into packets and routed over IP using routers and gateways. And each evolution, analog to digital to packets, adds capacity, flexibility, and complexity. And NG911 sits firmly in that packet-based world. So this section covered a lot of ground. So here's how we piece all this together. Telecom networks are built from several different layers: the transportation, the switching, the signaling, and the routing. Whether a call uses landline, a wireless device, or a VoIP application, their calls move through these layers before it ever reaches 911. Legacy networks used copper loops, circuit switches, tandems, and interoffice trunking. Wireless added mobility with spectrum, so radio frequencies, handoffs, LTE, and the IP multiplex subsystems. VoIP introduced packet routing, call servers, gateways, and URIs, which we didn't talk about URIs, but that kind of looks like an email address, but it's actually the phone number of the destination you're trying to reach. And then all of these technologies feed into the 911 system through selective routers, which use location data to send the call to the right PSAP. Transportation media included fiber optic, microwave, satellite, coax, and copper, which supports the underlying reliability of every route the call needs to take. And all of this history explains why NG911 is such a transformation shift. We're moving from a patchwork of legacy technologies into a unified IP-based, geospatially driven emergency communications environment. Understanding the legacy side helps you appreciate the challenges and the opportunities ahead as Canada's transitioning to the future. And that's all I have. So I want to open up the floor to any questions you guys might have. Again, I know this was quite a complex topic this week, lots of acronyms and technology, but definitely recommend you read through the body of knowledge, rewatch this recording, and you can always email executive@nenaontario.ca if you have any questions, and we'll be sure to get those answers for you. So I just want to open it up to the floor if you guys have any questions at this time.
I have a question. Can you tell me the capacity, is that decided by CRTC, or is that something that's decided by the individual carriers like Bell and TELUS? And what I mean by capacity, what's the threshold where people call in and they get a busy signal or any other thing?
Yeah, I don't have that answer right now, Doug, but that's a great question. Frank, is that an answer to the question? Or is that a new question?
Yes, correct. According to Bell, Tom mentioned there was no limit, but the limits are determined by each individual agency. So depending on your system.
Okay. Yeah, so I think this is a two-parter. So if we're talking about regular phone network capacity, that I'll have to get an answer for you on who determines that and how it's determined, which is a great question. When we're talking about bandwidth to a PSAP in an NG911 environment, our network providers that are providing the 911 network look at call volume to that PSAP, and then they significantly increase the bandwidth requirement for that PSAP to ensure that the NG911 environments are working properly. But from a network capacity perspective, we will get that answer for you, Doug, and we'll share it with the group.
Thank you.
Any other questions? Okay, well, thank you everyone for taking the time out of your Wednesday night. Thank you for being accommodating to switching to Wednesday instead of tomorrow. Really appreciate it. This is, of course, recorded, so will be available in the shared drive, both the recording and the presentation. And please feel free to reach out to, like I said, executive@nenaontario.ca with any questions you guys might have. Happy studying, and we'll see you all next week. Actually, sorry, Jamie, do we have a meeting next week? Or is it not to the new year now?
Let me double check now, but it's probably not to the new year. Yeah, correct. So the next one's on.
It looks like there's one on the 30th, possibly.
ENP study. There is one on the 30th,
Yep.
yes. So nothing
Okay,
next
so
on
perfect.
Tuesday.
So nothing next week. Enjoy your Christmas, everyone. And then it does look like our fourth session is going to be on Tuesday, the 30th at 6 p.m. Eastern. So we'll see everyone there. Thanks, everyone.
Thank you.